So we had seen last time that the derivative of the inverse map is d by dx of 1 by x is minus 1 by x squared. So d by dx of 1 by x evaluated at x equal to a is equal to minus 1 by a squared. And the general statement for matrices is that if we saw that if I and V is a map from invertible matrices, if I and V is a map from invertible matrices to the space of all matrices, then the derivative of the map I and V at a point A in R evaluated at a point H in R, this is equal to minus A inverse H A inverse. And I had made this comment that just try and prove this in terms of partial derivatives, even in the case for n equal to 2 or 3. And even in the case for n equal to 2 or 3, you're going to have lots and lots of problems. You will not be able to show this. So this is probably a very glaring example where you have to be able to think of the derivative as being a linear map between two vector spaces. And by the way, calculating the derivative for more complicated functions is something that is going to be central in very large parts of mathematics and physics and chemistry. Lots and lots of sciences, you have to talk about the derivative of more and more complicated functions or maps between more and more complicated spaces. So this is an idea that you have to get used to. Okay, so the most important property of derivatives that we will be needing is what is called the chain rule. And what is the chain rule? So we have all seen again, essentially in school or high school, we have seen, for example, a statement which says that d by dx of cos x squared is equal to 2 times cos x times minus sin x. So I'm using a chain rule which we have all seen from school days. And what this says is that if f is from R to R and G is from R to R, f G composed with f prime at x is equal to G prime at fx multiplied by f prime at x. So this is something that we have seen earlier. And the statement we want for the chain rule is exactly this statement in several dimensions. So what is that statement? So what is the chain rule? So let f be a map from what we had last time was Rn to Rk, and G a map from So let f be a map from Rn to Rk and g a map from Rk to Rs. And we are going to assume these functions are differentiable everywhere. Then, what is the chain rule? We'll say that if A is in Rn, then the derivative of g composed with f at A is equal to, so I should write this in a bigger font, the derivative of g composed with f at A is equal to the derivative of g at f of A multiplied by the derivative of f at A. Notice that all these things actually make sense because the derivative of f at A, g composed with f, is a map from Rn to Rl. So this quantity is an element in linear maps from Rn to Rl. This quantity, the derivative of f at A, is a linear map from Rn to Rk. And g, derivative of g, at some point is a linear map from Rk to Rl. So this is something which will take Rn to Rk, and this is something which will take that element in Rk to the element in Rl, which is what you have here. Okay? So this is what the chain rule is. And we'll be needing this in quite a few places, and actually this is more complicated than it appears at first sight. Because just think of what we are trying to say. It is useful to write this out also in terms of partials. What do I mean by that? So suppose f is on n variables, that is x1 dot 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 xn, and it takes values in Rk. So the components of f I'm going to call f1 up to fk. So this is f1 x1 xn, f2 f1 xn, and fk x1 xn. So the variable in this Rn, I'm calling it x. The variable in this Rk, I want to call y. So the variable here is y, and the variable here I will call z. G of y1, yk has how many components? It has L components. So G of y1 to yk is equal to the components of G I will call G1. How many are there? There are L of them. So this is G1 of y1 yk up to GL of y1 yk. Close bracket, close bracket here. And therefore, if I call H equal to G composed with F, H is a function which takes n variables and gives you k variables. So in fact, what should I be writing down? H of x1 xk, sorry, H of x1 xn is equal to G of f of x1 to xn, which is f1 of x1 xn, comma, fk of x1 xn, which is equal to, Now I'm going to write that in this way. So this is equal to G1 of F1 of x1 xn dot Fk of x1 xn. This is the first component. Similarly, I'll have the second component, and then I have the nth component, GL of F1 of x1 xn, comma, Fk of x1 xn. I hope I can break the, I hope I have put all the enough brackets there. I think I need one. With this expression, try to find the derivative of h in terms of its partials. And this is something that you have seen for small values of n. And for larger values of n, it is going to get more and more complicated. And therefore, this is another example where you must think of the derivative as being a linear map. And this business that we have here, multiplication, is composition of linear maps. So we will need this in a little while. So let's stop here. So it's good to it's good to write down some functions and you apply the chain rule. And apply the chain rule in this way for several variables. If you think of it in this way, there's a 101% chance that you will get it wrong. So please do try this. We now want to talk about what are called the higher order derivatives. So what is it that we know? We know that if f of x is, for example, x to the 7, then f prime of x is equal to 7 x to the 6, and f double prime of x is equal to 7 into 6 into x to the power 5. So what is it that we are doing? The second order derivative of f is that h of x equal to f prime x, then h prime of x is equal to the second the derivative of the first order derivative is called the second order derivative. This is what we have all seen in our more elementary classes. This is exactly the idea that we want to do. Remember here, the second order derivative for functions from R to R are in fact a number. And therefore, because they are a number, we can talk about Taylor's theorem and all the higher order expansions of f around something. So, now we take f from Rn to Rk, and suppose it is differentiable at a. So, h of x is equal to derivative of f at x. Where is x here? I'm assuming that this function is differentiable at every point in Rn. So this h, remember, is a function. From where to where? The x itself that I have is in Rn. So h is a function whose domain is Rn. And where does h of x lie? H of x is the derivative of f at x. Where does this lie? So as we have said, this is a linear map from Rn to Rk. So h is a map from, its domain is Rn, but its range is linear maps from Rn to Rk. So remember, this is some Rn, and linear maps from Rn to Rk is also a n times k dimensional real vector space. So this also is some real vector space of dimension n times k. If the derivative of h, if it exists at a point, is called the second derivative of f at that point. So definition, a in Rn, and if derivative of h at a exists, derivative of h at a, I should be more careful here, so let me be slightly more careful. Derivative of h at a is called the second derivative of f at a. So the derivative of the first derivative is called the second derivative. We already know what we mean by the derivative of a map. Okay, it is a linear map from this vector space to that vector space, depending on the domains on which this is defined, domain and range. So the question is that suppose the second derivative exists. Where does this what is this second derivative? Okay, so this actually is a bit of a confusing thing to think about. So you have to spend a little bit of time to convince yourself that where is the second derivative of f, or where is the first derivative of h, where h itself is a map from Rn to this space. But what do we know? We know that if f is a map from Rn to Rk, then the derivative of f is a map from, derivative of f at a point x is a map which is a linear map from Rn to Rk. So for h, the Rn is the same, but the Rk gets replaced by the range gets replaced by linear maps from Rn to Rk. Once you have this clear in your mind, then you should be able to understand that, then note that the derivative of h at a, which is the second derivative of f at a, is an element of, I need a bit more space, so let me write this again. The derivative, the second derivative of f at a is an element of, it should be what? It should be linear maps between something and something. So it must be a linear map from this space, Rn, and it should be a linear map from this space to this space, whatever I have on the other side. That space is linear maps from Rn to Rk. So the second derivative of a function at a point is a linear map from Rn to linear maps from Rn to Rk. So this is actually a very difficult idea to digest, but it is something that you will have to get used to, because these are the kind of objects that we will be playing around with for quite some time. So once we know what the second derivative is, it should be clear what the third derivative is. What is the third derivative? The third derivative is the derivative of the second derivative. And therefore, if it exists, yeah. Here again, you should ask yourself the question, what happens when n is equal to k is equal to 1? If n is equal to k equal to 1, this is linear maps from R to R. But there's an identification of linear maps from R to R to be a real number. So L1, LR1 to LR1 is just R. N is equal to 1, so that becomes linear maps from R to R, which is just R. So the second derivative in the case when n is equal to k is equal to 1 is actually can be represented by a real number. N equal to k equal to 1. L linear maps from R to linear maps from R to R is actually represented, can be represented by R itself, by a real number itself. So what we had done previously is consistent with this, or actually I should say what we are doing now is consistent with what we had done for n is equal to 1. So the second derivative of f at a point is a linear map from Rn to linear maps from Rn to Rk. Therefore, what is the third derivative? The third derivative is the derivative of the second derivative. So if the third derivative exists, where does the third derivative lie? If you have understood this correctly, then the second derivative of f, g of x, equal to second derivative of f at x, is an element in linear maps from Rn to linear maps from Rn to Rk, and therefore this function g is a map from Rn to linear maps from Rn to linear maps from Rn to Rk, and therefore, so the derivative of g is called the third derivative of f, and the third derivative of f, where does it where does the third derivative of f lie? So the third derivative of f lies in, this is the derivative of g at a, is an element in linear maps from Rn to linear maps from Rn to linear maps from Rn to Rk. So I close this bracket, then I have to close this bracket, then I have to close this bracket. This is a place, so we'll continue from here.